So our next speaker is back to biology. We are have Dr. Liu Ya-Wen from National Taiwan University Institute of Medical Medicine, and she's going to tell us about lipid.
Yes.
So welcome.
Thank you. I'd also like to thank the organizer to give me this opportunity to share with you the rest of work in our lab. Is also cell biology is interconnected and membrane, and so therefore it is seldom possible that they are involved. But the story I'm going to share with you today is that after a new computer project that is studying the liquid composition and there's a little worm here. It actually evolved from bacteria with the endosymbiotic process. And it's therefore is a double membrane structure and generates most of the energy, chemical energy that we need to power our cellular reaction. And mitochondria are dynamics organisms that undergo constant fission and fusion process. And its morphology is dependent on the fission fusion process balance. And the morphology of the mitochondria, the tubular or fragmented status, reflects not only its energy status, but also its phosphorus reaction activity. That means the tubular the mitochondria are, the higher the oxidative they are. Therefore, mild stress or starvation would actually promote the fusion of mitochondria to become higher acid reaction to produce more ATP or energy. On the other hand, when mitochondria is depolarized or under severe damage, it actually will become more fragmented in order to the subsequent process like metabolism or apoptosis in order to maintain their function. So with this proper dynamic, mitochondria can maintain their good quality, and you can easily imagine that this regulation of mitochondrial dynamics would actually remain different kind of human disease, such as neurodegeneration or so in addition to many proteins that responsible for the mitochondrial fusion and fission process can be regulated by the numerous cellular demands in order to drive this dynamic. Some lipids has also been found to be critical for the regulation of mitochondrial movement. And one of the most important is plasma lipid. Plasma lipid is the signature lipid of mitochondria, which is synthesized and enriched as mitochondria in the membrane. And looking at the structure, you will be able to see that a very striking difference from this structure from other lipids in our membrane. The plasma lipid in our membrane mostly composed by one cholesterol backbone with two acyl chains. But look at the plasma lipid. It actually has two phosphoric acid connected by one glycol backbone. Therefore, it is a lipid with four acyl chains. So very striking and very unique geometry that make it a very good critical structural lipid in the mitochondria in the membrane to form the crystal structure and to have the respiratory chain supermolecule complex have the optimal activity. In addition to this structural role, plasma lipid has also been found to be a signal lipid that drives the fusion and fission process. In the mitochondria in the membrane, the collagen will bind with the mitochondrial fusion machinery in the OPA1 and facilitate the mitochondria in the membrane fusion. However, when mitochondria is under a little bit depolarization, collagen will be externalized to the outer membrane of mitochondria, where it binds to the mitochondria division machinery, the YAP1, to stimulate its binding and assembly. So it's doing right here. The polymerization of the YAP1 to drive the division of mitochondria. So it actually conducts two opposite functions when it's membrane for fusion and outer for fission. Interestingly, in 2006, a group in Stone group, Michael Farman, they found that when plasma lipid on the outer membrane encountered by phosphorylase DN9 or another name PLD6, it will be catalyzed from this two phosphoric acid moiety into phosphoric acid. And the phosphoric acid would actually promote the clustering and fusion of mitochondria. Very interesting but it remains unclear what is the molecular effector of binding protein for phosphoric acid to promote or drive the mitochondrial fusion. So with the following data, I'd like to share not only the skills that or experiment that we conduct in our lab, but also try to convince you that the new role or the new missing piece of the puzzle, the binding partner or the effective protein for phosphoric acid to drive mitochondrial ultimate fusion is MME3. So what is MME3? MME3 is a member of the nucleoside phosphate kinase that analyzes the GTP formation or GTP synthesis by transfer phosphate group from the ATP to GTP. So function as a GTP fueling enzyme, MME family member has been found to provide the energy source for many GTPase to drive membrane trafficking or some other stimulating events. As for MME3, actually back to 2019, Professor Zhang Zhifeng at our institute discovered that MME3 is localized to the mitochondrial outer membrane, essential for the fusion of mitochondria. But surprisingly, in a kind of independent manner, indicating that the old model, the fueling enzyme model, doesn't fit in for MME3 to drive mitochondrial fusion. So how exactly MME3 is? So we collaborate and take a closer look at MME3 and find MME3 is different from other MME family members, have a unique amino acid composition. And this composition is equipped with hydrophobic movement propensity. What is hydrophobic movement? It is ability to form amphipathic helix, the unique structure for alpha helix of protein that has the ability to bind to lipids. To test its idea, we found that indeed the N70 amino acid of MME3 is sufficient and essential for the protein to target to mitochondria, and with mutation to disrupt the amphipathic propensity of this helix with lipids or disrupt its ability to bind mitochondria, and utilize in vitro recombination recombinant protein mixing with a biconditional liposome to demonstrate that the full-length MME3 indeed can bind to liposome composed of phosphoric acid but not conjugated. And furthermore, this liposome binding approach dependent on its antenna and also amphipathic helix formation. And using some genetic tool, we also found that indeed MME3 function downstream of the PLD6, producing enzyme of phosphoric acid. And next, we utilize optogenetic to increase the phosphoric acid amount of mitochondria or siRNA knockdown depletion, but amount of TLD6 in the cell to increase or decrease of the phosphoric acid level of mitochondrial automatically. We found that indeed the N70 targeting mitochondrial efficiency actually regulated by the amount of phosphoric acid automatically. Okay, but there's a problem here is that according to the structure predict for the PLD6, it has its catalytic site facing outward. So it has been proposed for years that theoretically the phosphoric acid should be catalyzed on the opposing membrane of the mitochondria, which where the PLD6 localized. So indicating that if the MME3 targeting to mitochondria is controlled by the amount of phosphoric acid, it should be at the contact interface. I hope you can tell me, but I will show you the record data. So we conduct lifestyle imaging to follow the distribution of MME3 itself, and we indeed observe a significant enhance of the MME3 GLP signal when two mitochondria contact with each other. And interestingly, this kind of intensity increase is the ability of MME3 to bind to phosphoric acid ability. So because of limited time, I would like to show the last piece of the data that we demonstrate that MME3 is tethering complex to hold two mitochondria to stay associated. So we utilize the conflict again to demonstrate that in the presence of MME, we can pull two liposomes together and that can be see clearly on the active scan and that those liposomes can be tethered together with the addition of amino. And we also visualize purified mitochondria, and if you with amino, you can find that the mitochondria with green or yellow would associate together in the presence of white amino, but not oligomer mutant or the lipid binding. So overall, we find the missing piece of puzzle that is selective to tether the damaged mitochondria with puzzle lipid crystallization and to promote selective fusion between damaged mitochondria and therefore to maintain the homeostasis or quality control of mitochondria. So finally, I'd like to thank our collaborator, Professor Zhang in our institute, also to tell you two different states of ages. And last information is about our current need, a call for help is that we hope to have the lipid probe that would be easy to use to detect the externalization of carbon to the ultimate grid. Because so far, the most convincing way to detect carbon externalization is by mass spectrometry to detect the carbon after the ultimate refraction of mitochondria. So there's no easy way to detect, and we are actually trying to develop some protein probe or fluorescent tech probe to detect the carbon, but we haven't had good progression. So any comment or suggestion or idea would be highly appreciated. So with that, I really thank you for your attention and happy to have your questions. Thanks.
Thank you.